Chapter 5.1, The Balancing Act. Okay, let's dive into this. Welcome to our explainer for this chapter. Today, we're going to fundamentally change the way you see mathematical averages. We're going to look right past the raw numbers and actually discover the physical geometry that's hiding inside our everyday math. So, think about this for a second. What does an average actually look like? Now, I know we usually think of averages as just numbers, right? Just a totally predictable result you get at the very end of an equation. But I really want to challenge that whole rote memorization of formulas. Just imagine for a moment that this mathematical concept actually exists in a physical space. Like, if you could literally hold an average in your hands, what shape would it take? How would it behave if you pushed it around? All right, before we build this entirely new mental model, let's just do a super quick recap of our baseline. We all know this stuff. The mean is simply the sum of all values divided by the number of values in your dataset. Easy. And the median, well, that's just the middle value when all your data is sorted neatly from smallest to largest. It's completely straightforward, standard textbook math. But here's where we make a huge pivot. We are moving away from that familiar arithmetic formula on the left side. Just crunching numbers, adding them up, dividing them out. Instead, our new objective is finding the visual, geometric center of the data. We want to actually see the mean in space, not just calculate it on a calculator.
Let's start with a really simple setup. We've got two data points, 3 and 7. Now, the old way of calculating tells us, okay, 3 plus 7 is 10, divided by 2 equals 5. But visually, and this brilliantly illustrates our point, notice that the mean of 5 sits exactly halfway between the two numbers on the number line. It's the literal physical center of those two dots. It is a perfect point of symmetry.
Now, it's incredibly satisfying when it's just two numbers, isn't it? I mean, everything is perfectly symmetrical, it's neat, it makes sense. But let's raise the stakes a bit. What happens if we have three numbers? Or what if we have a completely scattered, totally uneven collection of data points where that beautiful symmetry is just completely gone? How on earth do we find the geometric center then? And that brings us to a really crucial question. Is the mean always just the exact midpoint of our extreme values? Just think about it for a second. If you have a bunch of numbers spread all over a number line, does the mean just sort of lazily split the difference between your absolute highest number and your lowest number? Well, actually, scratch that assumption, because the answer is no. The mean isn't just the midpoint of the extremes. For example, if we plot 6, 7, and 8, the mean is 7. But notice the physical distances going on here. The left-hand side has one dot that is exactly 1 unit away from the mean. The right-hand side has one dot that is also exactly 1 unit away. Imagine a seesaw. The mean is acting as the fulcrum, where the left and right distances perfectly balance each other out. So let's test this seesaw metaphor on something uneven. Let's say we have dots scattered at 2, 4, and 9. The standard calculation tells us the mean is 5. So is 5 the exact midpoint of our extremes, 2 and 9? No, it's not. But look at the total distances. On the left-hand side, the dot at 2 is 3 units away from the mean. The dot at 4 is 1 unit away. 3 plus 1 equals 4, right? Okay, now for the right-hand side. The single dot at 9 is exactly 4 units away from the mean. Aha! The total distances are absolutely equal. The left-hand side distance of 4 perfectly matches the right-hand side distance of 4. So the mean is acting exactly like a fulcrum, balancing physical weights on a seesaw. It's totally brilliant. And now what's really interesting about this slide is that even when things get incredibly messy, this underlying geometric rule absolutely holds firm. Whether we densely stack a bunch of dots on the left or we scatter them completely randomly across the entire board, the physical distance on the left side of our fulcrum will always perfectly equal the right. You don't even have to get bogged down adding up every single fractional distance. The core concept is what matters here. The sum of the distances on the left literally always equals the sum of the distances on the right. So, breaking it all down, the absolute crucial point we need to take away from this explainer is that the mean is not just some cold, abstract calculation. It is a physical balancing point of distances. Imagine literally dropping a heavy boulder onto our seesaw. If you insert values greater than the mean, it pushes the right side down, which means the balancing point has to physically shift to the right just to maintain equilibrium. This is exactly why, say, a single billionaire moving into a small town drastically shifts the average income. They're acting as a massive, heavy weight on the far right side of the seesaw, pulling the mean right along with them. And conversely, inserting smaller values adds weight to the left, sliding that fulcrum back to the left. So we've completely decoded how the mean behaves as this physical balancing point. We've seen it dynamically shifting and adjusting to every single new piece of data we throw at it. We know exactly how the mean shifts, but how does the median react? How does merely finding the middle value balance the scales when those heavy outliers are dropped onto our seesaw? Well, I am going to leave you with that mathematical mystery to ponder. Thanks so much for joining me for this explainer, and keep visualizing those numbers.